Hey guys, today we're going to look at a really one of these short questions, the 7-point questions, and this one's interesting because it brings together three different subjects. And so we've got this block P, and it has mass m. It's on a frictionless surface, and it's oscillating back and forth with on a spring with a spring constant k. It has a period of t sub p and an amplitude a sub p, and that's the equilibrium position. This second block is dropped from rest and lands on block P at the instant it passes through the equilibrium position. Easy for me to say. So block Q immediately sticks to the top of block P, and the two-block system oscillates with period Tp and amplitude APQ. Okay. Now this is from the 2018 administration, so you can look up the rubric if you'd like. You can grade me if you would like. Anyway, we want to first determine the numerical value of the ratio of the period after the collision to the period before the collision. Okay. To do that, we're going to have to use the formula for oscillations. Tp equals on your formula sheet, it probably will say T sub S, but I'm saying T sub P because we're talking right now about block P. Okay, and so that's just 2 pi times its mass, which was m, and over the spring constant, which was given to us as k. Okay, now when Q lands on top of it, the total mass of the system changes to 3m, and that would be, so it would just be 2 pi times the square root of 3m over k. So to find that ratio and to evaluate that, you would just divide those two things. So I would put this in the numerator and that in the denominator. The 2 pi's would cancel out. What I'm going to do is I'm going to rewrite this as the square root of 3 times the square root of m over k, so it's easy to see that the square root of m over k drops out, and you just get the square root of 3. After I did this problem, I looked, and that was only 1 point. And this is a 7-point question. So obviously most of the points are going to be in the next part, part B. Part B asks how the amplitude of oscillation of the two-block system compares with the original amplitude when this block was all alone. Now, even if you check the correct answer here, that's not even another point. It's all about the clear, coherent paragraph length response. Now, I've posted about how to write an effective paragraph length response to Schoology. I really want to encourage you guys to go ahead and read through that, get some practice at it. We've talked about it before in class as well. Anyway, first thing you want to do is answer the question. So I'm going to answer, and I'm going to say that amplitude is going to be smaller. Okay, and then I want to provide some basic physics and cite some evidence, and then draw it all together. That's my ABCD. So the first thing I did was I answered the question, and then I'm going to do the rest. Okay, so the first thing I said was the system's total mechanical energy is elastic potential energy at the amplitude, right? That's where it is stopped, and the spring is stretched out. But the collision's inelastic, so some kinetic energy was lost, meaning some of the total mechanical energy is lost. Now, since the total mechanical energy is less after the collision, the elastic potential energy is smaller at the amplitude. Now, elastic potential energy is 1/2 kx squared. K doesn't change. In order for the elastic potential energy to be smaller at the amplitude, x has to be smaller. Okay? So therefore, APQ must be less than A sub P. The amplitude afterwards is less than the amplitude that we began with. Now, a couple alternate things you could have said was that at this equilibrium position, the energy is totally kinetic, and that with this slamming into this, you're going to lose some of that kinetic energy. Therefore, you're going to have less kinetic energy. And if you have less kinetic energy here, you'll have less elastic potential energy at the amplitude. Less elastic potential energy at the amplitude means a smaller displacement. All right, guys, I hope that was helpful. Stay safe.